In section 3.6, we will explore one-to-one functions and also talk about what inverse functions are and talk about how to compute them. First, let's look at what it means to be a one-to-one function. A function f is said to be one-to-one if different inputs have different outputs. That is, if a is different from b, then f of a must also be different from f of b. Another way to say this is that in the ordered pairs that make up the function, no two ordered pairs can have the same x value, and no two ordered pairs can have the same y value. Let's look at the following two functions and determine whether they are one-to-one or not. First, we have f of x is equal to negative 4x plus 12. Well, this function consists of ordered pairs that form a line. I'm going to do a basic sketch of the graph. We have a y-intercept at 0, 12, and we have a slope of negative 4. And so this is a rough sketch of what that line looks like. If we take a look at the ordered pairs on this line, we see that no two ordered pairs would have the same x-coordinate because we don't see any ordered pairs that are vertically aligned. We also don't see repeated y-coordinates because we don't see any ordered pairs that are horizontally aligned. Therefore, this is a one-to-one function. Next, we have f of x is equal to the square root of 25 minus x squared. Now, the graph of this function is going to look like the square root function with some transformations applied. Here, we see that there is a possibility for the same x-coordinate to produce the same y-coordinate. Let's do a quick table of values to show you that we have a problem with this one. Let's say, for instance, that x is equal to 1. When we substitute 1 in for x into the rule, we see that f of x is equal to the square root of 25 minus 1 squared, or the square root of 24. Now we can simplify this further, but let's just keep it in this unsimplified form for now. Now let's say, for instance, that x is negative 1. We see that by substituting negative 1 into the rule for f of x, we get the same y value. Now, while it is possible to have repeated y values and still be a function, it's not possible for there to be repeated y values and for it to be a one-to-one function. So it is a function, but it is not a one-to-one function. What this means is that you could have repeated values in this case for y, which makes it a function, however, not a one-to-one function. In the next couple of examples, we will look at the graphs. Here we have a quadratic graph for letter A, and the question is whether this graph represents a one-to-one function or not. Well, we already talked about the vertical line test for determining whether the graph of a relation represents a function. Back then, we said that a function must pass the vertical line test so that no vertical line intersects more than one point of the graph. Clearly, this is a function because it does pass the vertical line test. However, there is another test for determining whether a function is one-to-one, and that is the horizontal line test. The horizontal line test says that no horizontal line can intersect more than one point on the graph. Clearly, we see a violation here in this example. This horizontal line intersects two different points of the graph. Therefore, the function is not one-to-one. The two ordered pairs that I have put asterisks at have the same y-coordinate. For the next example, we have a piecewise function, and We do see it's a function because it is going to pass the vertical line test. No vertical line is going to intersect the graph at more than one point, so it is a function. Now let's see if it's a one-to-one function by trying to apply the horizontal line test. If we can find a horizontal line that intersects more than one point, then it will not be one-to-one. But I think we're okay. Even this horizontal line that I'm adding here in red, it's only going to pass through one point, this solid point right here that I'm darkening. Notice that while this point has the same y-coordinate, it's not part of the graph. It has an open circle, which means it's simply a placeholder. That means that in this case, it is a one-to-one function. So why do we care about whether a function is one-to-one? Well, one of the applications is that a function will only have an inverse if it is one-to-one. In other words, one-to-one functions have inverses. Functions that are not one-to-one do not have inverse functions associated with them. So let's talk about what inverse functions actually are. If a function f is one-to-one, then f inverse, denoted with a -1 superscript. It looks kind of like an exponent, but it is a label, is the unique function such that each of the following holds. The composition of f inverse with f is equal to x, and the composition of f with its inverse when evaluated at x is also equal to x. I like to explain this concept with a little bit of a visual aid, so just bear with me. Suppose that the function f is like a machine. It takes an input, and the input is what we call x. F does something to that input. It processes it in some way. And as the output, we have y, which we also denote as f of x. Those are synonymous. So that's our output. Now suppose we have a different machine that pretty much reverses whatever f did. Let's call that f inverse. Now the input for f inverse is going to be y, which is the output that we see above. From that process, we have a new output, and that output is going to be x. Now, if you can follow this analogy, we start out with x, it undergoes some process and becomes y, and then after it becomes y, we circle y and put it into a machine that reverses that action, and we end up with x. This idea is what we see here when we compose f with its own inverse. One of these two is the direction that I've talked about here, and the other one would have just the opposite order. So we'd be going through the process in the reverse order. Either way, what this is saying is that we have done two actions, one original action to x and one that reverses that action, and so what we end up with is x again. So if you think about an inverse function as a function that reverses whatever actions were applied to x to begin with, this should help you understand conceptually that composing a function with its own inverse will get you back to your original input of x. Now, let's show this composition as an example with f of x is equal to 5x plus 8 and f inverse of x equal to x minus 8 over 5. So we already know going into this example that f and f inverse are inverses of each other. All right, let's do some composition. First, let's compose f inverse with f of x. So the rule for f inverse is that we take the input subtract 8 from it, and then divide it by 5. F of x is equal to 5x plus 8. So we'll make that substitution here. And so we get 5x over 5, which simplifies to just x. So that shows us that the first requirement is met. Next, let's compose f with its inverse. The function f multiplies 5 times the input and then adds 8. Well, the rule for f inverse is x minus 8 divided by 5. Here, we can divide 5 by 5 and get 1, so we get x minus 8 and then plus 8. So again, we get back to x. So we see here that the second requirement is also met.